Good afternoon once again. So I would like to start by readdressing a particular statement which has been made in my previous talk. I'm getting to understand that some people still probably they miscoded the information while I was talking about the recent development about the compartmental modeling of malaria. So I made mention that according to the biology of malaria, there is no need to include a compartment denoted by R for malaria. And the reason being that we are not saying that people do not recover from malaria. People do recover, but the kind of recovery they are, the kind of recovery they have does not grant immunity. Okay. So the recovery does not grant immunity, either temporary or permanent immunity. I hope that is clear. People do recover from malaria, but such recovery does not grant either permanent or temporary immunity to infection. So, and as such, it means that there is no period in time in the transmission of malaria that somebody will be in a recover class, such that the person cannot be infected by malaria even after bite. So that is the point I was trying to make then. So I hope that clarifies that. So today we'll be talking about some qualitative analysis of compartmental models. So we have introduced some compartmental models to us. So starting from SIR model without demography, which we say that this kind of model is suitable in the study of an epidemic disease. Then the model was later extended to SIR model incorporating demography. And later we considered some specific some model addressing a particular disease. And we were able to look at that of COVID-19 and also malaria. So we want to see, even though our main focus could be on the quantitative of analysis of any model we come up, since we want to make a data-driven study so that we'll be able to inform a data-driven policy. However, it is also important that we look at some of the qualitative properties of whatever model we build, because based on the theory of differential equation, our model must be able to satisfy certain properties. Okay, so in this discussion we are going to be focusing on equilibrium point, next generation method, and specifically the spectral radius. And then we also talk briefly on stability analysis. Then the question will be that why do we need to do this? And why are we limiting ourselves to this? There are many things there are many analyses we can carry out on a model, but it is considered that these are very fundamental. Okay? Okay, in order to save my time, so so we will pick so I will make use of the board throughout this talk. So can I have the first slide? Okay. So the equilibrium point, why is it necessary for us to find the equilibrium point of a dynamical system, particularly the compartmental model we have come up with? So an equilibrium point of a dynamical system is a state where the system, where the variable of the system, pardon me for that, where the variables of the system or component are balanced and there is no tendency for change over time. So that gives the definition of an equilibrium point. That is the state at which there is no variation in the variables involved in the model. So in epidemiological models in particular, so since that is the focus of our talk, we are considering epidemiological models. There are two equilibrium points that we usually look at, and these are disease-free equilibrium and endemic equilibrium. So what do we mean by disease-free equilibrium and endemic equilibrium? A disease-free equilibrium is an equilibrium state of a model in the absence of disease. So that means we may want to study the equilibrium point of a model at disease-free when there is no disease in the population. And this is important because in order to study the dynamics of an infection, we need to look at two different scenarios: when disease is not in the population and when the disease is in the population. So when we know what happens when the disease is not in the population, it will help us to know what happens when disease is in the population. So for the endemic equilibrium is the opposite of disease-free equilibrium. So to mean an equilibrium state in the presence of infection. So why finding the equilibrium point of an epidemiological model? Why do we need to find the equilibrium point of an epidemiological model? One of the reasons why we need to do this is that we may want to predict the behavior of whatever system we are looking at. So if we want to do that, it is necessary we understand the equilibrium point, which help us to predict how systems will behave over time. So that's one of the reasons why it is necessary to look at equilibrium point of a model. So by finding the equilibrium point of a model, it will also help us to analyze. Analyzing equilibrium point also help us to determine the stability of a system. In other words, if you want to study the stability of a model, it is important we analyze the equilibrium point of that model. And lastly, equilibrium point can be used to optimize system performance or outcomes. So in other words, we may want to look at the behavior of a model with respect to any intervention being incorporated into the model, as we know that the presence or absence of an intervention is expected to affect the dynamics of a model. So as such, studying the equilibrium point of a model will help us to optimize the system performance on outcome with respect to whatever the focus, our interest is in the model. Okay, so in order to summarize the first two basic models being introduced, the SIR model without demography and SIR model with demography. So since the analysis followed the same pattern, so I want to focus on the SIR model with demography. So we are all familiar with this model. So we have the total population being compartmentalized into three, where we have susceptible individuals, we have infected individuals, and then we have recovered individuals. And the susceptible individual, people are recruited into the population which is strictly susceptible through birth. And then transmission occur due to the interaction between susceptible individuals and infected individuals at the rate beta. Then it is assumed that after a certain time, people do recover from that infection at rate gamma. And then people died at any point, regardless of any state being regardless to the compartment that an individual belongs, such person can die naturally. So looking at that flow chart, we have the governing system of differential equations as given in equation 1. And I want to believe that this is clear to all of us. We can remember that we said the rate of change is equals to inflow minus outflow. We said this. And when we will take a look at the compartment S, the only thing that brings people into this compartment is through what? Is birth. That means the rate of change of S with respect to T will be equals to what? What is coming in, which is what? Which is lambda. And what is taking people out of that class is what? Is transmission. At what rate? At beta. So and whenever an arrow is going out of that compartment, it means what? Outflow. So we have minus beta times I times what? Times S. Then we've also included natural death rate. If you look at that, natural death rate is also one other thing that takes people out of that compartment. Then we also have minus mu S. Is that clear? So we are able to derive the ordinary differential equation that govern the dynamics of susceptible individuals over time. Also, for the I class, we have beta. People are being progressed to that class at the rate beta, and people are moving out of that class due to recovery at what rate? At rate gamma. And then people also die naturally at rate mu, so that the I, the T becomes, people are moving into high at this rate, then we are going to have beta IS, and people are going out due to recovery at rate, then we have minus gamma I, then people also leave that compartment at what rate? Due to natural death at rate mu minus mu I. And this gives the rate of change of infectious individual at any time T. So, and lastly, we have for the recovered class, people progress to recovery class at rate gamma, so that we have the rate of change of R with respect to T to be gamma I, and people leave that compartment due to natural death only, isn't it? So minus mu R, and as it was said the other time, for this kind of disease, we assume that after recovery, the person become permanent immune to that disease. So, and this is what I said the other time, for in the case of malaria, people do recover, but there's no, the kind of recovery we have is not infection blocking immune. As such, there is no point in time that anybody will be in this class. Because even though you have recovered from malaria, does not mean that once you have a mosquito bite, one cannot be contracted with the cannot get the infection again. So that is what I said the other time, which I've also clarified now. So we are able to get this system of equation from the model. So if we want to look at the equilibrium points, for us to find the equilibrium point of this model, I will always refer to this as equation 1. Okay, let's suppose I'm using this model to solve to address the dynamic of a particular disease in a location. As this model being well presented as it is, let's say, for instance, I'm using this model to study the dynamics of measles in Nigeria. For instance, just to say, if I present this model as it is it okay? Why is it not okay? No initial value. Thank you for that. Because the only thing that will make this model to speak to a particular location is that it must have what? Initial condition. So for instance, if I have the y dx is equals to, let's say the y dx plus 2 sine, okay, let me say plus 2y is equals to sine x. If I give this differential equation, what kind of solution am I expect to get? A general solution. It does not speak to a particular scenario. But immediately I pose an initial condition, y of 0 is equals to 1, for instance. What solution am I going to get? I will get a particular solution. That means I'll be able to use that model to address a particular scenario. So as such, I need to put the initial condition to this model. So I must have my initial condition given by s of 0 greater than 0, I of 0 greater than 0, and R of 0 is equals to 0. And I ask, is that my initial condition correct? Is the initial condition correct? What is wrong? S of 0? I didn't put. Is the initial condition correct? Is it correct? Who is responding to my, okay? Okay, who is responding to my question? Is the initial condition correct? Are you talking? Is the initial condition correct as being posed? Why is it not correct? Okay, R of 0 to be greater than or equals to 0. And that brings up another question. Why should R of 0 be greater than or equals to 0? Okay. 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 So if people recover from an infection, let's say R is equals to 2. It means 2 people have recovered from that disease. It means that at least 2 people have been infected. Is that? And that establishes the fact that the disease is what? It's endemic. It's endemic. And you remember, we are looking at endemic situation. R of 0 equals 0 is correct when the disease is what? Is an epidemic. Is that clear? If you look at the model for an epidemic, in that case, R of 0 is equals to what? It was equals to 0. But in this case, it must be greater than or equals to 0. Okay? So now we have this model. We want to find the equilibrium point. We want to find the equilibrium point, and like I said, to find the equilibrium point, we have two of them. Disease-free equilibrium and what? Endemic equilibrium. And like, can I see this slide, please? Oh, okay. Next. No, not here. Okay, the pointer is working. Okay, thank you. Okay, so we first of all want to look at the disease-free equilibrium of this model. So to obtain the disease-free equilibrium of model 1 or any compartmental model, so it is first requires that we set the right-hand side of the model equation to 0. You remember the definition of equilibrium point of a dynamical system. That is, when there is no variation in the what? In the component or variables of the system. There's no variation. That is, the rate of change is what? Is constant. As such, the rate of change will be equal to 0. In order to comply with that definition, we are going to set the right-hand side of each of these differential equations to 0. So that we have this to be equal to 0, to be equal to 0, to be equal to 0. Then, we also recall the definition of disease-free equilibrium and endemic equilibrium. We said that disease-free equilibrium is a system steady state when there is no what? When there is no disease in the population. As such, to find the disease-free equilibrium of this model, having set the right-hand side of each of the equations to 0, we also need to identify the infected compartment. What is the infected variable here? Is I. It also requires that we set I to be equals to what? To be equals to 0. So let's see what happens to that system if we set I to be equals to 0. The first equation, we have lambda minus beta into 0s minus mu s is equals to 0, right? The second equation, we have beta times 0 times s minus gamma plus mu times 0 is equals to what? Is equals to 0. And lastly, we have gamma times 0 minus mu r is equals to what? Is equals to 0. If I simplify this further, the first equation will result to lambda minus mu s is equals to 0. Beta times 0 is 0. This, we have this to be 0. Then gamma times 0 is 0. As such, mu r is equals to 0. And consequently, r is equals to what? R is equals to 0. I can therefore say that my disease-free equilibrium is equals to S star, comma, I star, comma, R star, which is equals to what? Okay, I have a resulting equation here, which is lambda minus mu s. What am I looking for? I'm looking for s. And at steady state, we have that mu s is equals to what? Is equals to lambda. So if I make s the subject of the formula, what am I going to get? I will get lambda over mu, and consequently, It will mean that disease-free equilibrium, which part? B times 0. We have lambda minus beta times 0 because I is 0 times S minus mu S equals 0. Okay, so if you multiply this term will become 0. And that was what I said the other day. This one. So beta times 0 times S. No, for the second equation. You know we have 3 equations. So if you now solve this, we are going to have this to mean lambda over mu, comma 0, comma what? Comma 0. And this gives the disease-free equilibrium. Okay, so the S star, you can see that we have moved from S to S star because we are looking at the solution at equilibrium point. It is no longer S. It becomes a solution, which is a solution point, isn't it? So that in order to distinguish between S and the equilibrium solution, we change that to become S star because that solution was obtained at equilibrium point when there is no variation. You said? Yes. In fact, immediately I was looking at equilibrium point. All the variable will change to S star, I star, R star at equilibrium point. So thank you. Hello? All right, thank you. Okay. So with this solution, we can make many insights from the dynamics of that disease being represented by the SIR model. So next we look at the endemic equilibrium, which we said that this is an equilibrium when there is disease in the population. Okay, we made an assumption or hypothesis in the case of disease-free equilibrium. And what was that hypothesis? That the infected compartment is equals to what? Is equals to 0 because there is no disease in the population. In the case of endemic equilibrium, it first requires setting the right-hand side of all the model equation to 0 because we want to look at the solution at what? At equilibrium point. And that will take me to have, I will rewrite that again. I will have lambda minus beta I star S star minus mu S star equals what? Equals 0. Then I will have for the second equation beta I star S star minus gamma plus mu I star equals 0. And lastly, I will have gamma I star minus mu R star is equals to what? Is equals to 0. But for me to make the difference between disease-free equilibrium and endemic equilibrium, I can use a different notation. Maybe I make this to be I star star, S star star, and R star star. So that there will be difference between the disease-free equilibrium point and endemic equilibrium point. So, and we also have, can I see this slide, please? Okay. We do not set the infected variable to 0 in this case because the disease in the population. So if that is the case, we will need to solve the entire system as it is. How do we do that? For a simple model like this, it is very easy to explicitly express the solution in terms of the model parameters. It is very easy. So We will see how we do that. If you look at this, we are looking for what? The solution for S, I, and R. So it is very convenient for me to start from the second equation of this system. If I say from the second equation of that, from 2, you know that I'm going to have beta I. So permit me to retain I as I star, S as S star star, and R as what? R star star. Just permit me to do that for simplicity. So I have beta IS minus gamma plus mu I equals 0. From here, we have a common factor. What is that common factor? Is I. I can have this to mean beta S minus gamma plus mu into I equals what? Is equals to 0. You remember that hypothesis that I cannot be 0. It implies that since I cannot be 0, then beta S minus gamma plus mu is equals to what? Is equals to 0. For the product of two terms to be 0, either of them must be 0. Or both is equals to 0. But in this case, both cannot be 0, since I cannot be 0. So if I cannot be 0, it implies that the other term is what? Is 0. So if that is the case, we have that beta S is equals to gamma plus what? Plus mu. If you rearrange this, keeping with the aim of making S the subject of the formula, we are going to have this. So that S is equals to gamma plus mu over what? Over beta. If you look at this, it will be minus. Okay, so if you look at this, if you have to find to simulate that model, what are the inputs that we need? The inputs. We want to find the numerical simulation of the SIR model. What are the input values that we need? Beta and gamma? You want to solve a system of differential equation numerically. So what will be your input values? All the parameters? Is that all? What about the initial condition? Initial condition. So if you look at this, I can know my S numerically as long as I know my model parameters. Isn't it? Which will be readily available. That means I'll be able to get the solution explicitly in terms of the model parameters. For instance, gamma is the recovery rate. That is biology, right? I must have been able to establish that. Mu is a demographic parameter, which is a life expectancy. I can get that. Beta is the transmission rate. It's either fitted to the data being available or taken from what? From literature. So, meaning that I'll be able to get my X explicitly in terms of the model parameter. But this is not the case for every compartmental model. When the model becomes complex, you may not be able to, in most cases, you won't be able to get your solution explicitly in terms of the model parameters. Okay? So, since we know that I is not equals to 0, I can get my I. Where do I have I and S? From the first equation, right? So, okay. So from the first equation, I can get my I, and then from the last equation, having gotten my I, I can also get my R. So So from the first equation of that equilibrium system, I can have that lambda minus beta is minus mu s is equals to what? Is equals to 0. I've known my s. I'm interested in this. I can have beta is to be equals to lambda minus mu s, right? So from here, I know what s is. I will have beta I times gamma plus mu over what? Over beta is equals to lambda minus mu times gamma plus mu over what? Over beta. Let me ask. Beta, okay. Yes. So from here, I will have I into gamma plus mu is equals to lambda minus mu into gamma plus mu over what? All over beta. Let me ask first. Can I have a negative solution for a disease model? Can I have negative solution? Why is it that I must not have a negative solution? Women are not what? Human beings are not negative. Eh? I is greater than 0. Going by the initial condition as well. Okay? So if that is the case, we have from this last expression that I is equals to lambda over gamma plus mu minus mu into gamma plus mu over what? Over beta times what? 1 over gamma plus mu. Is that correct? Okay. If I'm correct, I will have this to be I equals lambda over gamma plus mu minus mu over what? Over beta. Isn't it? And you said my high must be what? Must be positive. Okay? I can simplify this further to mean I have mu over beta into bracket lambda over gamma plus mu times beta over mu minus 1. Is that correct? If I factor mu over beta, is it correct? Okay, if that is correct, then I can simplify, neatly put this as mu over beta into bracket lambda beta mu into gamma plus mu minus 1. Okay, then I place an emphasis. Now put, so what is that? What is that? What is that? It's a threshold, right? Oh, so it's a threshold. And we said the solution must be what? Must be positive. What if I choose this such that this value is less than 1? Is it not possible that I supply the value of lambda and beta, mu, and gamma such that the numerical value I'm going to get is less than 1? Is it not possible? It's possible. And if that happens, what am I going to have? I will have the result becoming what? Becoming negative. That means there must be an imposition such that this guy must be greater than what? Must be greater than 1. So we will continue from there to see what this threshold. Okay, you can find from the last equation, we have gamma I is equals to mu r, such that r is equals to gamma over mu times what? Times I. We've gotten I. just multiply the result for high by gamma over mu, and we are able to get R. So we will talk more about this threshold as time goes on. There's another concept aspect where we are going to see how we can explicitly determine this threshold that will make the endemic equilibrium to be positive. So for today, I want to stop here. Thank you so much.